which is the pendulum lab. The pendulum lab. While you're getting that out, I am going to hand out the packet that you will need for the written assignment, which is due Thursday. We're going to start Unit 2. If we have time, we'll get it started today. If not, definitely tomorrow. But this is the Unit 2 packet that you will need to do the assignment that is due Thursday. In your Google Classroom, there will be a couple of videos on Unit 2A, which we'll learn about just a little bit. And then you're going to answer the questions on pages 1 and 2 of this packet for Thursday. Go ahead. Mr. Walter.
Hello.
This is our period 5 class. Mr. Walter, folks, this is Mr. Walter. He is a substitute for our high school. He's certified in physics and mathematics. So if I'm ever out, you'll be meeting him if he's available, because he can actually do real physics stuff with me while I'm out. So you won't be getting busy work. You'll be just continuing, which is always a good thing. So we have a full house here. Just one empty seat. Noah's not here today. Anyone see Noah? No? Okay. So, you must stay too long.
Right, and I'm done. I'm sorry.
That's okay. Thank you. All right. Everybody set? Everybody have Lab 3 open? Okay. So let's get going here. Lab 3, the pendulum. Let's just review where we got what we did last week, because you'll need to remember this in order to help you answer the questions today. So remember that we started off in our first experiment on Friday. We varied the mass at the bottom of the massless string, and we measured how much time it took for it to swing back and forth 10 times. You'll see that the Google Sheet then calculated what's called the period, which is the time for one swing. And then we made a graph of the period versus the mass. When we modified our graph, we got rid of the units in the title. We added a 0 to the horizontal axis, so that way we had a vertical y-axis on our grid. We added the trend line and the equation for the trend line. Your graph should look like a horizontal line if you've done that correctly. Experiment 2, we built these 5 pendulums, but instead of changing the mass, now we changed what angle we were pulling it back from. And then we measured the time for 10 swings. The Google Sheet calculated the periods for us. We then made our graph, where again, we modified the title to remove the units from the title. We added the 0 on the horizontal axis, so that way we have a vertical grid line there. We added our trend line and the equation for the trend line. Again, the graph looks like a horizontal line, if you've done it right. In the third experiment, now we kept the mass the same and the angle the same, and we changed how long the string was. Again, measuring the time for 10 swings. The Google Sheet calculated those periods for you, and then you made a graph of the period versus the length of the string. You modified the title to remove the units. You added the 0 on the horizontal axis, so you have a vertical grid line. You added the trend line, which in this case turned out to be a power series curve, and then you added the equation for that trend line. Good so far? Everything looks the same? Okay, let's now talk about the analysis. The first question asks, based on the data that was collected, which variables seem to affect the period of the pendulum the most? There were 3 variables. We tested the mass, we tested the angle of release, and we tested the length. Which one seemed to affect the period the most? Yes, and how do you know? Yeah, so there's 2 ways we can see it. Number 1, from the graph, we see that we get this parabola. Secondly, when I look at the data table, I can see that that has the greatest variation in the periods recorded, where everything else just changed by a little bit from trial to trial. Very good. So let's go ahead and answer that question in the yellow space. The length affects the period the most. I know this because in the data table, there was the greatest variation in the periods, and in the graph, and the graph was a parabola instead of a horizontal line. Those are the kinds of things that you're looking for. You can answer it in your own words, but you are telling me, number one, how you can see it from the data in the table, and the other evidence you have from the graph is that you have a parabola instead of a horizontal line. Let's see if I make this a little bigger. There we go. Do you have to write down exactly what I said word for word? No, you can paraphrase it, put it in your own words. Okay, we good? Okay, question 2, based on that graph. So we're looking at the period versus length graph. What's the relationship between the period and the length? So when you look at this, what shape did we say that was? A parabola. What's the relationship on a graph that's a parabola? Quadratic. Very good. Yes, you have to know that for your test Wednesday. So there is a quadratic relationship between period and length. Okay, question 3 is going to require a little bit of modification to your graph. So let's talk about that. You ready? Okay. Question 3 is asking us to use the graphs to make a pendulum that has a period of exactly 1 second. Exactly 1 second, 1.000 seconds. In other words, I want to know what mass would you be putting at the end of the pendulum, what angle, and what length. To do this, because you said it's the length which is determining the period, you're going to have to look at your graph of period versus length, the one from experiment 3. You're going to have to look at yours. You're going to have to make some modifications. I have to make this smaller. We're all going to have to modify our graph a little bit. The reason we have to modify our graph is because we do not have enough grid lines, vertical grid lines on this axis, so that way we can read off a value when the period is exactly 1 second. So basically what we need to do is read this graph at 1.000 seconds. Go over and then come down. But based upon the grid lines that we have, it's impossible to determine what that length is with any kind of precision. Okay, and we want to be accurate. So here's how we can modify that graph to get more grid lines. Go ahead and double click on your graph. And when you do that, you get your chart editor. Go under the customize submenu on the right. I want you to come down to where it says grid lines and ticks. Grid lines and ticks. Now, please change this to the horizontal axis. So we're going to modify the horizontal axis. And what I'd like you to do is scroll down even a little more. There's an option for minor grid lines. Check that. Do you see as soon as you do that, it gives you more of these vertical lines coming up? I'm only seeing 2. So I have 1, 2, 3 divisions to get me to 0.25. That's not a nice, easy scale. And it's still very difficult to read off what that value would be right here. So we can add more of those grid lines by making a change. Come up here. You see it says minor spacing type, the count, and the minor count. We're going to leave this to count, but over here, we're going to say how many grid lines we want. We want to have a total of 9 additional lines between the 0 and the 0.25. So as soon as I do that, and I go from 0 to 0.25, notice I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 subdivisions to get me to 0.25. As soon as I've done that, now every line is 0.025, which means you can get a length with a fairly decent amount of precision. Now my curve is about halfway between the 9th and the 10th grid line. You have to look at yours. And you can enlarge your graph. If you go here, you'll see a percentage window. You can zoom in. You can zoom in on your graph to make it larger so you can try to read the value with greater accuracy. Do you understand what I'm saying? Then you can just come down. You can use your calculator if you need to figure out what that middle value would be. So for example, if I'm one line over here, this line, one line over here, that is 0.225. And that is 0.250. So I have to figure out what is that middle value. And because my simulation is not going to allow me to go out to that level of precision, I'm going to have to round it. So based on my calculations, mine's about 0.2375 meters, but I can't go that precise, but that's okay. So what I'm now going to do once that has been modified, I can then come over to the analysis and try to type in the parameters that I want for a mass, an angle, and a length. So in terms of a mass and an angle, what I have to do is go back to my first data table for this experiment, experiment 3, and read off what mass did I use and what angle did I use. So I'm going to use the same values. Those will then get typed in here. So I had a mass of 0.7 and an angle of 9. The length is whatever you're reading off your graph at a period of exactly 1 second. So I should try to get 0.2375. I don't think the simulation is going to allow me to do that, so I have to go to 0.24 meters. And that's just fine. Okay. So get your values. You have to use your graph. I'm going to be looking at your graph. If your graph doesn't give you that value, I'm going to be taking off points. I need you to read your graph to see what your graph tells you you need for a period of 1 second. Okay, once you have that figured out, you're going to open up your Pendulum Lab, the simulation. And each of us needs to do this separately. So I'll give everybody a minute to get your simulation opened back up. And set it up. You need a stopwatch on there, not a ruler. And what I want you to do is build the pendulum that we just designed. Build the pendulum you said you needed with the mass, the length, and the angle. So I'm going to go ahead and modify mine so I have the correct length, which was 0.24 for me. This isn't group work. This is individual work. Each of you has your own thing to do because it's based on the graph that you got. So you have to come up with your length, your mass. Oops, there it is. And my angle. There it is. I'm going to release it. Now, what I want you to do once you've built your pendulum in the simulation that you said you were going to test, we're going to test it, but you're not going to time one swing. How many swings did we time Friday? 10. I don't even want you to time 10. Bryce, I want you to time 30 swings. You know all how to time that? 30 outs and backs. So go ahead. You're going to do that for yours. You're going to get a time. Okay. Now, if you've done this well, 30 swings, we wanted it to have how much time for one swing? 1 second. So how much time should we have expected to get? 30 exactly. You're not going to get 30 exactly. I don't think so. I got 29.70. Hopefully you got something really close to 30 if you did this well. What I now want you to do with that time, go back to your Google Sheet. The time you just measured, I want you to put that in for the MV, the measured value in question 4. 29.70 seconds. Make sure you follow it with a unit. So we're now going to do a percent error calculation in question 4, where the accepted value was 30.00 seconds and the measured value is 29.70 seconds. You can see I want you to use the guess method. I've lined this up for each step. So what am I asking you to calculate? What's the unknown? Percent error. So we're going to type that in, the percent symbol followed by the word error. The equation is on your reference table, but I'm going to type it right here. So this is percent error equals. Now you need the vertical line, which is above the backslash. It's above my enter key on my keyboard. So shift and the vertical line for your absolute value, then in parentheses, AV minus MV. That's accepted value minus measured value. We're now going to close the absolute value. Then we're going to divide by the accepted value. And then we're going to multiply by 100%. That formula should look familiar to you. Right? We've been writing that before. Let's see if I can make this even bigger. If I do 200%, it's going to be too big, I think. Let's see. It's probably good enough. Okay, so now let's talk about the substitution with units steps. So we're going to do percent error equals absolute value. Then in parentheses, you now have to type in the accepted value. We all have the same accepted value, 30.00 S for seconds. Minus, now you're going to type in your measured value, followed by seconds. Make sure you include the units. Close your parenthesis. Add the vertical grid line or the vertical line for absolute value. Then you're going to divide by the accepted value. We're all going to divide by 30.00 seconds. And then we're going to multiply by 100%. Now you got to go to your calculator. You all have a calculator handy? You're going to need your calculator to do that percent error calculation. You're going to give me a percent error with 2 significant figures. And when I do the calculation, I get 1.0%. Is that good? Is that a good percent error, 1%? What do you think? Yeah. In a lab, in physics, we typically like to get less than 5%. So 1% for me is excellent. It means I read things well off my graph and so forth. All right. Once you have that percent error calculated and entered, make sure you hit enter to get out of that cell so the Google Sheet will save your work. And then you can submit the lab and the lab is done. Yeah. Okay, because in the numerator, we have to subtract first. So I'm pretty sure when you subtract, you're going to get something that's like out to the hundredths, probably a tenths value and a hundredths value. That's 2 sig figs. You probably have a 0 before the point. I don't think anybody's going to get anything off by more than a second. If you are, then you would have 3 sig figs. Because it would be like 1.05 seconds. That would have 3 sig figs. I would like you to do it too. Yes. Yeah, so get it from the data table and just turn it. Yeah. Means your length probably is not measured correctly off your graph. That's probably what that means.
So for cases when like there's multiplication, subtraction.
Yeah.
Which takes priority?
You have to do order of operations with math. So the first thing you do in mathematics, you do what's inside the parentheses. So in this case, you would have to do the numerator to do the subtraction. So that would take the precedent. And since my subtraction gives me two same things, my answer would have to.
So like it's like the first thing that occurs in like any like equation or something. I think we do that.
Okay, I'll leave that up there for a minute so that way you can all finish up the lab. When you have finished this up, I'd like you to put your Chromebook away. That's a signal to me that you have submitted your lab. Make sure you turn it in. Don't just finish it. You have to go back to Google Classroom and hit turn in. And once you've done that, then we can take out the following items to get us ready for Unit 2.
Eric, you better put my name for that.
So this would be 0.30, and that would be 0.2.
It's really the exact same as same exact layout.
Again, once your lab is done, I need you to put away your Chromebook, pack it up. That is your signal to me that you are done with the lab, and I can then move on to start Unit 2 with you. And for Unit 2, you're going to need a notebook, pencil, calculator, and your reference table. Yeah. Here, so that is about 2.375, but you have to run it 2.24 as a simulation. So you go to your length, and there you need a 0.24 meters. think I have to push something else out for everybody. I don't think it was going to post until tomorrow. I got to add it. Okay. Jacob, we'll just do that quiz tomorrow. Okay. What's up? All right, ladies and gentlemen, let's shift to Unit 2. Unlike Unit 1, I am not doing this with any PowerPoints. I'm going to be writing things out. We're going to be basically tackling Unit 2's discussion because I think most of what we're tackling in Unit 2 you've probably learned about back in middle school. All right, so it's easier for me to do this more as a discussion than it is to just say, here's a bunch of slides, let's go through them. Okay, so that is my goal. We're going to tackle Unit 2 as a discussion and getting things written down. So Unit 2, the title of this unit is Uniform Motion. And it begins the study of something in physics that we call kinematics. Kinematics is the study of how things move. We're not going to concern ourselves with why they're moving the way they do, just how are they moving. This is actually going to bring us all the way through Unit 5 of our course, where we're going to break down the motion into different kinds of motion. The type of motion we're dealing with in Unit 2 is the simplest of all of them, where things are moving uniformly. That means with a constant speed. Okay. So Section A of Unit 2, so Unit 2A, is all about the terms position, distance, and displacement. And as we learn about these physics terms, we're going to obviously introduce a lot of vocabulary, but we'll also talk about the mathematics that you need in order to solve for positions, distances, and displacements. So let's start with the first term in that list, and that is the term position. When we refer to an object's position, we're talking about where an object is located in an XY coordinate system. So I'm mentioning the XY coordinates. That means I should be able to make a sampling of an XY coordinate system, where that is the positive X, that is the positive Y, that is the negative X-axis, this is the negative Y-axis. If I had an object located right there, and let's say this was at a position of 3 meters on the positive X, and the Y coordinate, it went up 3 meters as well. Let me change that. I don't like where I put that one. Let me fix it. Let me move it here to 4 meters. I would say that the x coordinate in that diagram was positive 4 meters. That positive signals that we are to the right of the origin. And our y coordinate would be listed as positive 3 meters, where that positive sign would signal that we are above the origin. So when I ask for an object's position, you're going to have to tell me in what direction you are from the origin. So if you just said you were located 4 meters for your x coordinate, I wouldn't take that. Because I'm just saying, okay, what does 4 meters mean? It means you're 4 meters away from the origin, but you didn't tell me you were to the right of the origin. You just said you were 4 meters away, which means you could be to the left of the origin. Do you understand the difference? You need the positive sign in front of it to indicate the direction you are away from the origin. The x coordinate, we will abbreviate with an x. The y coordinate, we will abbreviate with a y. These types of measurements that we see that include not just a number, but a sign, where a sign is giving you a direction with respect to a reference position, in this case, the origin, these are called vector measurements in physics. What is a vector measurement? A vector measurement always has two things. A vector measurement will always have first what we call a magnitude, where a magnitude refers to a size or an amount. In this case, the size is 4 meters. The y coordinate, the magnitude was 3 meters. It's the amount, the size. But the second thing it will always have is a direction. And in these measurements, the direction is given with the positive sign. In a moment, we're going to talk about different ways we can specify the direction. It's not always with a positive sign. So what we're seeing here, because I'm giving you these positions with direction and magnitude, we would say that position is a vector quantity. Meaning when you state an object's position, you need to give me not only how far away you are from the origin, but in what direction you are away from the origin. Okay. Is everybody with me so far? Makes sense so far? That's about as simple as I can make this. Let's then talk about different ways we can specify direction. Let's draw an XY. Oh, we'll stop here. We'll pick up with more of this with direction tomorrow after we go over your Unit 1 review, which is due tomorrow. All right. Have a wonderful day, folks.